Good morning everyone. So let's welcome to the last day of our Dhyan session. I hope you organized yesterday and last night and now you are set for the last day session. So today's session is more about characterization and so on and all those things. Particularly most of the part we have discussed. So today the session where interesting folks among us will discuss about different IP and CV characterization, some troubleshoots, and we will tell you about the use of the PSI tool, how you can use the PSI tool to extract the data, device or material data after the IP or CV characterization, how to do characterization. And once the session will be over, then we'll walk to our lab again and we will walk from the B1, we will walk to our lab, we will have some small hands-on on the IV characterization using the PSI SMUs and basic station. So basically, today among us, over the application engineer of LMAC, Mr. Vimal Raj, he has around 15 plus experience in application of PSI product range. Also, he has a solution expertise in material management characterization etc. He is based on our Chennai office and heading application team in India. So, Mr. Vimal, thank you for giving your time. Thank you for joining us. Slowly over to you.
Thank you. Is my screen visible?
Yeah, your screen is visible, so just please make it full screen.
Okay, now?
No, still your desktop is coming. So it looks like you are sharing multiple monitors or something. Because full screen presentation.
No, sir, now I open only one.
Sir, is it fine? Yes. Okay, it's fine for the no problem. You can go ahead in this also. Still not full screen, but the areas are fine, no problem. Yeah, please go.
Okay. Good morning, everyone. I am Vimal Raj. I am from application engineer from the LMAC engineering service. We are doing the testing and measurement solutions we are using. Over the past 30 years, we are doing the same techniques and some other engineering brands also. Most of the people allow the PSI brand and a small introduction. Not only for IV characteristics and PSI with a wide portfolio users with us for all types of electrical and electronic testing measurement equipment. We have a solution which is effectively part of the interface instruments like the multimeter, kilometers, output, processors, platform, and we have all products and we have a material characteristics like that, and we have a cost segment that is various products in this data. We have given the full solution to a lot of customers also, a lot of higher level of semiconductor industries also we are doing, and we are doing with the production areas also we are given the solution. Okay. This is not part for the segment introduction. Today we are going to discuss about the fundamentals of IV measurement. What are the fundamental steps we want to follow to achieve the IV measurement? That's something we are going to discuss. Okay, most people are aware of IV measurement, IV characteristics like that. Okay. From the basics, for example, if you want to see the characteristics, okay, if you want to see the characteristics, you need the voltage versus current. Each and every.
Are you changing your slide or you are still on your profile?
Change it, sir.
No, then I think something problem then. Your slide.
1 second.
Please reshare again. Please reshare your full screen. I think better if you share your full screen and then you go to presentation mode. I hope you are using only one monitor.
Now it is.
Now okay, but it's not in full screen mode. I can change it and see the full screen change or not. But still full screen mode is not there. share the desktop, then only it will work. You have shared presentation, I think, or it's not.
Now it is.
You share full screen. You stop the sharing, and then you want to better you stop it sharing and reshare your full screen. Then you go your PPT presentation mode.
Okay.
Save your full screen, and then share go presentation in the mode. Then you go. If you are using only one screen, then multiple screen, then again problem. Now you will presentation mode. Perfect.
Okay.
Change the slide. Yeah, perfect. Now you will,
Okay.
Thank you.
Sorry for the inconvenience. Okay. When you are going to speak with, normally you want to see a character fitting the linearity of voltage versus what will be the corresponding current will be there. Like that, we have see the voltage and measure the current. It will be happen on the all type of instrument. We are seeing the voltage. If you want to see the voltage, okay, if you want to see the accurate characteristics, it's more important than using the sample. How many steps we are splitting? That also is important. If you are splitting 10 samples, we can't get the exact curve. It will be the linear means we can get. It will be the non-linear curve, we can't get the turn-on voltage or turn-on condition. What will be the maximum peak? We can't be able to see the time frame and all of things. If we want to see the good characteristics, we need the more samples to prepare. In our equipment, we normally given the sample rate, what will be the sample speed we are given. Every 50 microseconds or 20 microseconds, we can be able to fix the voltage and we can measure the current. Like that, we can able to get the clear, high, accurate, and more resolution we can get in the curve. Okay. For example, in the resistors, we will do the linear circuit. If you go for the resistance, it will be the most unique voltage with respect to Ohm's law. With voltage, the current will be gradually increase. This is the linear curve. In the diode, we can see the non-linear curve. At some point of time, the diode will get turned on. And the reverse blocking also will happen in the course of the reverse bias. We can able to see the turn-on voltage, what will be the exactly with the 0.5 volt or 0.4 or 0.3. Like that, if you want to see, you can see and you can able to see. Same thing, similar it will be like that in the transistor, MOSFET, IGBT. Like that, we can able to achieve the measurement using this component or fabrication level like that. But if you want to achieve high accurate and low current and measurement, we are facing lots of struggles in the field. Okay, that's what we are going to discuss today. Okay, today is my agenda will be essential concept, what the concept they are using and what technology we are going to follow, how the source measurement unit will be plotted in the field, how to achieve the low current measurement, and how to measure the resistance importance of it, and some examples also I can show this today. First thing that is the most important, how accurate we are going to do the measurement or repeatability is there. What is the difference between the accuracy and the repeatability? In the lesson screen, you are getting more accurate. There are multiple rules there, but it will be the center means it will be more accurate. Okay. If you see the repeatability also is more important in the measurement. For example, if you are getting, for example, if you are getting or diode phase, then the total voltage telling us for the sample, theoretically your calculator will be the 0.4 volt. When you are doing measurement, it gives 0.3 or it will give, because of the repeatability will be not there, you are getting 0.3 or 0.4 or 0.5. Like that, each and every step, the different measurement will be there, we are not able to come into the conclusion. It creates a confusion. Okay. Then the repeatability will be there. For every time if you are doing the measurement, you are getting the 0.3. You are getting more reliable on the measurement. Then we can come into the conclusion. Okay. That will be the importance of the repeatability and the accuracy. In that accuracy, we want to do the more resolution, we can ensure the sample. And one more important thing, if you want to do the more resolution, you want to get the more ADC. If you the ADC will be higher, you can get more samples. In the block diagram, you can see the analog input. Whatever we are doing, this part will be happening inside the instrument. There will be the clock will be there, outcome converter will be there, convert to digital conversion. When your ADC bit will be increased, your sample rate also will be increased. Easily you can able to digitize in terms of 8 CPUs, it will be 40-56 steps on each processor. You can increase the ADC, now you can get more than the lakhs of data. You can easily plot the graph. This is the importance of the resolution. And one more thing, we are using lot of cables in the measurement. There are the normal wire, the EC cable, power track, power step-down wire, the rings like that, lot of people there. Most of the common tools we are using is the coaxial cable. If you want to achieve the resolution and the low current measurement or high resistance, you want to go with the two coaxial. There is a small example we are giving here. In the BAC, we are in the center of this cable will be the contact area, and for over the cable we are getting the insulation. Because of this insulation, we are getting 1 kilo x 10 to the power 9, and if we calculate that, we can get the resolution of 100 nanoamp. The same thing we can use in the triac. In triac, what will happen? They have one more filter will be there, it's a conducting rod will be there. Because of this conducting rod, we are avoiding the shield leakage. Okay. Using the shield leakage, we are avoiding, we are getting the resolution of same, it will be 1 kilo insulation, but same 100 volts, we are getting the resolution of 1 femtoampere. Okay. This is the importance of BLC cables and triac cables. If your length will be increased in the cable length will be increased, your losses also will increase. That time you can go with the triac cable. When you are doing measurement of less than nanoamperes, you need to go with triac only. Because when you get in the BLC cable, because less than nanoamperes, we can't able to achieve these very difficult. And one more important thing, we are using lengthy of cables will be there, the cable resistance also will be included. That's why we are using the 4-volt cable measurement. Okay? Because we are sourcing the voltage. If you are sourcing the voltage, the voltage will be travel in the cable. Maybe it will be travel 1 meter, 2 meters, 3 meters. Automatically, based on the sensitivity, the voltage will be getting dropped. Or you want to avoid the thing, you want to follow the changing method. What will happen is, they have a enforced terminal, the voltage will be applied. In the sense terminal, it measures the voltage, whatever the drop in the voltage, the equipment boosts the voltage. Maybe it will be 0.5 volt or 0.3 volt. The drop will be there, the boost the instrument will take care of the part, and it will be, we can, whatever the set voltage, we can achieve with the ends. We can avoid the cable resistance. Like that, the instrument having the back will be the force and sense. The force will be for applying and the sense is for measuring. In the cable will be of more than 1 meter, 3 meters like that, the guard terminal will come into the picture, wherever the leakage, that will be blueprint of the guard. Automatically your measurement will get accurate. And one more important thing for measuring the less than the nanoamp, and if you are measuring the high resistance, this is critical part. Okay. If we have a device, variable particle with resistance, if you want to measure the less than the nanoampere and picoampere or femtoampere, hectoampere, that time you want to follow the procedure. Okay. So what are the procedures we will discuss step by step. But at the same time, if you want to measure the resistance, the time also you want to follow, because the leakage, whenever the zone of high resistance, the current will be very less. Current will be in the nanoampere, picoampere. Automatically saturation will be there, so the resistance amount also will be reflected. It will be reflected mostly in the highly leakage will be there. Okay. I can give the basics of source measure unit. Okay. In the source measure unit, we have a architecture will be there. It acts as a voltage source and parallelly we can use the current source. This is normally called as the fourth quadrant measurement. Okay. There will be the quadrant positive voltage output from the negative voltage output from the same for positive current and the negative current. Source, current and the sink current. And a positive source and a negative source. Like that, fourth quadrant will be able to achieve using our SMUs. Okay. That's why if you see here, ideal voltage source also will be there, and the current source also will be there. In the series, we are connected with the ammeter, and then parallelly we are connected with the voltmeter. It will be registered in the fourth terminal only. Okay. And apart from this, we are connected with one more thing in the low terminal. We have options for cases, ground option also will be there. You want to do the measurement with respect to ground, or you want to do the measurement at the flow state. Like that also, you just can choose your option. Okay. Whenever applying the voltage, there will be the loop. Automatically, it will measure the current. The current flow will be happen. This current flow will measure, and the parallel we are measuring the voltage. And the same thing, if you change the current source and sourcing the current, and we are measuring the voltage. The same ammeter and voltmeter will take care of the measurement part. Okay. And how we are connecting, this is the combination for current voltage sources. When you are applying the voltage, you can vary from 0 volt to we have equipment can go up to plus or minus 210 volts. And the same thing for current, we can go from 0 to 3 ampere for current source is applied. And parallelly we can measure the voltage. When you are applying the voltage, you can measure the current. Like that, any combination user can do based on the sample or DOT. Okay. And one more important thing here, what is the advantage is when you are applying the voltage, the DOT may know how much current will be drawn. Okay. Sometimes the high current will be flow in terms of milliamps of the flow also, and the device will get burned. So current flow or maybe short circuit will happen. That's why we are given the option called current limit. When you are set the current limit, maybe it will be 1 milliamp or 1 nanoamp, the current flow reach the 1 nanoamp, will stop the current. More than that, we can't allow the current limit. Okay. Like that, it will be safety for the limit. And next one would be the basic class we are doing. When you are doing sweeping of the voltage and parallelly measuring the current, whenever we are measured the current, we are measuring the limit. When the current reaches the maximum limit, it automatically stops the sweep voltage. Beyond that, it will not go. Okay. And it will be same thing, it will be applied for the thin film or vapor, or it will be the component over the high power device also, it will be applicable. When you are using a LED, LEDs cover maximum current is equal, the light intensity will be increased, but it will be born. If you want to avoid the thing, you can follow the current limit. Then previously, now we have a SMU, we are easily achieving using two terminal positive and negative, we can easily achieve. But what previously they are using separately used multimeter for measuring the current and voltage, two multimeters, 1 meter for voltage measurement, 1 meter for current measurement, and a safety combination of voltage source and current source. For the current source, we are using resistive load and vary the load. Based on the load variation, the current source will be better. Using this combination of four equipment, they are measuring the IV characteristics. It's very, very difficult to do the measurement, and implementing the measurement also will be difficult. Now we are using the SMU. Okay, the SMU is a very compact tool. It's a single equipment. Just connect both positive and negative. We can be able to see the characteristics. Okay. So, like that, the technology upgradation is happening. Now we have some new equipment with multiple channels of the simultaneously captures up to 20 samples also is possible. In your wafer, we have multiple samples you are fabricated. Probably you want to see the 3 devices or 5 devices. It also is possible to test. Now the technology is totally changed and we are upgraded a lot of things. And our SMU specifications for basic concept and we have various models of SMU. There will be operated at 1 volt, 210 volt, or there will be combination of 3 ampere, 10 amperes, or etc. voltage ranges of that. And we have resolution is the most important thing. We can achieve using our SMU. We can go up to 10 control amperage is possible to apply. And same thing for voltage, we can measure the 100 nanovolt resolution. We can able to do for source and measure. And I told about the sample rate, and sample rate is now our equipment. We can see the based on the sample rate. Your fast measurement is possible to achieve. Mostly the fast means that will be used in the memory devices. Now there are lots of technologies are updated on the memory devices and how fast the transistors are going on, MOSFET or IGBT stuff on time. So how fast they are responding. That's why we need a high sample rate model. It will be useful in the high-speed devices. Okay. But there are various combinations will be there. We will start with later also. And also, when you are doing measurements, we have multiple combination of layout we can able to get in the graph. Okay. Here we are telling it's a constant. Okay. When you are applying the constant voltage, there is not able to see the turn-on time. It will be very, very difficult. Okay. That's why we are given up here linear speed. In the linear speed, we have two options. One is the single and double. For example, if you are seeing the linear single, it will be start from 0 volt to 5 volt. The same thing in case if your device having some capacitance will be there. When the linear single means you can't able to see the capacitance effect. When you put it in the linear double, you can able to see that what capacitance effect will be there in the sample. Maybe the transistors or IGBT MOSFET will have some capacitance effect. That also we can able to see in the linear double or logarithmic double. Because when you are speaking at the voltage, sometimes the small material will get charged. And the linear double, when you are sweeping down, we can get the hysteresis value that you can achieve using our SMU. And the same pattern we can use for the logarithmic speed. And logarithmic speed means that will be based on the 10x, then the plot will be switched. And you can see the characteristics. That will be mostly used in the RF measure, RF sample section. When you are discussing mostly you are using the linear. When you come to the RF component, they are using the logarithmic speed. Okay. And user dependent also is possible. In user dependent value nowadays people use most of the solar cell applications. They are using user-defined steps. They are following the principle. And whatever we are using is a DC. Okay. Same thing we can use with the pulse mode also. Why we need to use pulse mode? Okay. When you are using constant continuous applying the voltage or applying the current, your sample will be getting overheat. Based on the temperature also, your sample performance will be good. If you want to apply the thing, you can use the pulse mode. If I apply pulse mode, they have a get time limit. Every pulse, they have on time and off time. In the off time, the temperature will not shoot higher. It will maintain the temperature as the maximum we can able to follow. This is mainly in the vapor level component. Most of the vapor level fast response components are small. It will be 1 degree temperature is okay. Use variations we can able to see in the level. That's why we can use the constant as well as the variable as converting option is called as pulse. In pulse, if we use more maturity, we can get the characteristic. Next one is the most important, how to achieve low current measurement. What are the techniques we are going to follow? Okay. If you want to measure the low current, these are the problems. Exact and you should change in the actual measurement. When you are doing theoretical or simulations, you can easily tell you the value you can get from calculator one. But if you are doing actual in the measurement, there will be a lot of things you want to maintain and you want to follow the results. So, first one, how to eliminate the electromagnetic interference. When you are in your lab, maybe in the clean room, you can maintain the efficiency, not the clean room, it will be common for lab. There are lots of equipment available in the ground, laptop PC, or a high power transformer, or it will be the high power supply, and the collected of all the instruments also to read in the electromagnetic interference. And the next one will be the so you are doing the grounding in the power like a lot of grounding techniques will be there. It also affects the and measurements ranges will be there and noise, how to eliminate the noise and how to avoid the transmitter. We can follow the steps one by one. If you want to avoid the electromagnetic interference, you want to use the shielded box. Okay. Shield box is more important. It will avoid the external interference. If you use a cool environment, then automatically your duty gets isolated. It will not allow external interference to your sample. Because our sample also is a conductive. When you have external interference with the component also, it absorbs the energy. That will reflect in the low current measurement. Okay. And like that, it will be the shielded box will be there automatically. You can avoid the external interference. And if you want to follow the proper probing, based on the probing, you are getting achieve the easiest layer, one point of measurement. And the second one will be the grounding. Grounding is the most important thing actually. Now, most of the people are aware that I can extend the grounding method. When you are using, normally if you are doing the measurement or test lab, they are user of the UPS power. Okay. If the UPS are not ground, it's not grounding, it is a floating. Okay. Then the UPS method will come under the filter, your voltage is the floating, not grounded. Like that of the situation, what will happen? The grounding not proper, your measurement will be getting saturation in this. If not, will be the constant, your measurement will be getting saturation. It keeps zigzag like that you are getting. Maybe it will be varies from 10 nanoamps to 20 nanoamps, keep on saturation. Like that of effect also will be because of the volume. When your loop will be floater, first image, left side image is equivalent to the floating. When you connect the sample will be in the automatically will take the closed loop. Now, when the closed loop is commented, the current flow will be get properly set to be the one direction. It will be not grounded or multiple grounding also. It will be leakage of multiple parts will be also getting reflected in the measurement to avoid multiple grounding. Use one closed loop system. One closed loop system will get more accurate than steady current will. And next one is most of now that previously when maybe 10 years or 20 years back, our instruments are in the manually we want to put the rate. For example, in multi-rate, but in 10 million rate, 20 million rate, 200 million rate, and 2 million rate like that, manually we want to choose. Now a lot of technology of it, that's why they are given us the auto rate. What is the difference between manual and the auto range? The auto range means what will happen? The instrument will search, the instrument will take care of the switching. Internally, it switches the range, and because of the switching, we are getting the transient effect. Okay? Because of the switching, we are getting the delay measurement. It's not very fast, it takes some delay. Because it's scanning from, because in the SMUs we have 10 different gauges will be there. It starts from nanoampere or microampere. In microampere also 1 micron range, 10 micron range, 100 micron range, like that. Various ranges will be there. It sits from 1 micro, 10 micro, 100 micro, like that. Each and every place it creates a transient effect. Okay? If you want to avoid those things, if we know the measurement range, we can choose the manual range also. It will be helpful for the measurement, and this manual range is getting more faster responsibility because it will be switching 9 ranges, it will take some time delay. It will be in the microsecond or millisecond, but that also it will be reflected in the measurement. Okay. If you know the manual range, you can choose manual range that gives the more faster and stable way. The graphic and able to see the dependent sequence. It can take a previous range to be there. Using auto range, what the 10 grams to 100 million, keep on fluctuation, keep on changing. When you choose the system, it will be measured only from 10 kilo to 1 nanometer. That is, user can easily, and you can take a stable pictures. And next, most important thing will be the power line model. Okay. This is it will be there in all applied AC input if most of these range instruments, it will be operated in the AC voltage, it will be to the volt operating for equipment, it gives the power line model. Whenever the effect will be there, because we are giving as an input into the AC, we are doing measurement into the DC. Lot of switching happening and a lot of semiconductors are there. The power line noise will travel from input to the measurement point. Okay. If you want to avoid the power line noise, we can change the sample rate. Okay. Otherwise, we can do the averaging the measurement. Otherwise, we can go over to the. You can access in what in my every 18 months, you can be able to adjust the PLC rating. If you adjust the PLC rating, the PLC also relevant to your averaging. If I change the PLC to 1 PLC to 10 PLC, the measurement will get averaging and stability. Why this is most important data? For information, whatever I told, I show it in the presentation. I use the time that type of 15 microseconds or 10 microseconds. Like that speed sample rate is that. Your sample will be the fastest means you can use the fastest way. Your sample will be in the millisecond response or will be in the time you are getting more samples. That also is reflected in the noise. Okay. That time, if you want to avoid that thing, you can go with the average. Average will be automatically you get 100 samples and it gives the average of 100 samples. If you take 10 average or 100 average like that, user can design. Okay. And next thing I told is the translator. When you are doing the measurement, when for example in the SMU, I can show there will be the switch. It can switch to voltage to current source. When you switch happens, automatically it will take some time for stability because when you are seeing here, when you turn off, there will be the slope will be there. It will be slope will be from 0. It will be for example, it will be the 2 volts from 2 volts to 0 volts. It takes time. It will be the fault test. Okay. It is for the same thing for turn on. When you step off each voltage, for example, if you split it from 0 to 30 volt or 0 to 5 volt, each step has a rising rate. Okay. For this rising, it takes some microseconds. If you want to measure the actual time of rising, it will give only the, it will not achieve the exact value. For example, if you do 1.1 volt, you will be level 1.1 volt, you want to give some time delay. It's a measurement delay we can do. In that measurement delay also in terms of 1 milliseconds or 0.5 microseconds, like the user can do that. Our switching response will be the 10 microseconds. Greater than that, it can mean we can able to avoid the fluctuation. This will be the concept we are given the measurement delay. Okay. Now when we keep the measurement delay, automatically your rising and falling is not reflected in the measurement. Okay. And one more important thing, that each equipment having the self-calibration will be there. Okay. And self-calibration means what will happen is when you are going to do the measurement, they have some stabilization time will be there. For example, in our product, it will be the warm-up time. We are given 30 minutes to 40 minutes, 45 minutes if you want to do that. After the query, whatever the specification we are given is 20 ampere. If you want to achieve, you want to give the stabilization time for the instrument. Okay, when you turn on and immediately you want to achieve the 10 ampere, it's not possible because there is a lot of components and a lot of capacitance, diodes, everything is there in the device. Okay, for the device, it will take 30 minutes to 45 minutes. After the query, the calibration will happen. After the query, whatever the space that will be able to achieve. Okay. When you turn on and immediately getting a lot of fluctuations you can able to see. Okay. That you want to avoid, you can do the calibration. The calibration also will have some timeline for stabilization of the equipment. Okay. And next one will be the, I told it will be the measurement range. The measurement range now, if you see in the picture, the measurement current will be the auto, it will be 1 microampere. How the measurement will be reflected, and if we choose the manual range, how the measurement will be reflected. It will be, what is the reference? It will be maybe the picoampere and it will be the femtoampere. Like that, the difference we can able to see in the measurement range. And for it will be the eliminating measurement noise, we are putting the average. Then right side you see the fluctuation, there are a lot of fluctuations because of the we are doing getting the average measurement. We can do the normal or manual or PLC or long short method, user different options available. Then you are getting the very smooth curve. Okay, in the left side you can able to see the smooth curve, on the right side you see the fluctuation. Okay, if you see the fluctuation also is the picoampere. Okay, but if you see in the left side, the current picoampere also we are getting the peak value, but your curve that is very smooth. Next one will be the feather delay. That also when we are giving the measurement delay, I said the measurement delay automatically the fluctuation also it can able to start. The method of triggering and the measurement delay and the PLC with everything will be reflected in the measurement. These things you want to follow. If you are doing the measurement in the less than the 1 ampere, If you are doing more than greater than nanoampere, this will not reflect. Okay. When you are doing measurement in the femtoampere, picoampere, or in the nanoampere, you want to follow this step. Okay. And next one, I think it will be more related to the resistance measurement. So now we are what we discussed more later on current and the voltage method. Now we are going to do the resistance measurement. When you are coming to the resistance measurement, we have it will be the Ohm's law. It will be, for example, if you are doing the Ohm's law, you are normally doing the resistance. Okay, then you are sampling the curve. The sampling have some area. It may be the square or rectangle, you have a width, depth, length, like that. But here some samples are in the structure. It will be the diameter, the equal to be there. Okay, then coming to the resistance, we can get the resistivity. It will be the area also will be included. Okay. It will be area will be included in measurement will be the volume resistance as well as the surface resistance. Like that, we can split the two different ones. Okay. We can measure the resistivity in terms of volume as well as the surface. Both is possible based on the pictures you are selecting. That is the main thing reflected in the picture. Okay. And the second most important thing will be the temperature. Okay, when I told doing the measurement, then you will be the continuously applying the voltage, continuously applying the current, your temperature is shoot out in your surface. Okay, that also is more important thing. Okay, then the problem will start in the temperature. Most of the places in the temperature will created heat problem. Okay. When you are doing I V is equal to I into R, correct, which will be reflected on the resistance dependent on the temperature. When you are doing that will be mainly for the reflected in the current, because the resistance varies automatically, the current will vary. The resistance also varying and it's not actually. Okay, and the power also will be increased. Okay, you want to follow this, you want to monitor the temperature also and how we can be able to stop the temperature rise. We want to follow this. Okay. Here we can see the calculating formula. When you are increasing the 0.1%, it will be 0.007 degree in the centimeter square per width. The reflection of the measurement we are getting 0.04 milliwatt. Okay, that's the variation we can be able to detect. This is 0.1%. Okay, in the width. If you will be the huge variation, you are doing some MOSFETs will be there, some IGBTs are there, and if you do it in the later level, the small change in temperature, there will be huge impact in the measure. If you want to avoid those things, you want to maintain the room also, there will be the atmospheric temperature also you want to maintain, and you want to maintain the sample temperature. This will be the effect you are getting in the room electrical effect, and that will be gradually increasing because of the millivolt with respect to time. Okay. The transient voltage pulse, if you are given you are getting the thermal effect very less. And the same thing you can use in the current source mode. When you are applying the current and parallelly using this Kelvin resistance measure, we are avoiding the cable resistance. In the cable resistance also, it will be reflected in the measurement. Okay, when you are using the current source will be increased automatically. Your losses will be reduced, and we want to avoid the stable resistance. We can use other SMU, channel 2 SMU, and we can do the measurement also if possible in the Kelvin method. Okay. And we going to give some examples for this SMU. These are the whatever I can explain previously. These are the things we want to follow to achieve the low current measurement. Now there is lot of semiconductor chips that will be there in the converter. It's a regulator IC measurement. How accurately we are doing the measurement. Okay, using our two-channel SMU in the DC-to-DC converter, we can one channel for input and one channel for output. When you are applying the voltage, the same channel 1 will be taking care of voltage and current, and the channel 2 will taking care of the loading. When you are all our efficiency of the converter, we can be able to see it at a time itself, we can be able to see the efficiency. Input what will be the voltage, parallelly what will be the output effect. Let's say the light regulation effect is able to see, load regulation effect you can see, what will be the delay, on-time delay will be there, that also you can able to see. That's a lot of things we can be able to see using our system, because we have a combination of 4 quadrants. We have able to source the voltage, and we can also be able to load the converter. For your DC-to-DC converter, it will be regulator supplying 3 volts, regulator will be there. We can more accurately want to see how resolution of the base. Sorry. And here there will be the common ground. In the common ground also, it will be not impacted in the measurement situation. That's why we are using the common ground. If you are doing the different grounds, the measurement will be getting shorter. You can't be able to get the constant measurement. Here I can show the graphical representation. Okay, with respect to voltage, what will be the input voltage and output voltage, how the performance of the relay. In our software, we can be able to keep the voltage as possible. When you are keeping voltage, the output will be constantly get operating voltage from 8 volt to 12 volt, and the current will be thinking for 500 milliampere. Like that, the stability of the converter will be there. We can even our equipment we can source from the resolution will be there. From the 8 volt we can get the 4-digit resolution. And exactly what will be the each step will be happening like that the graphical representation also easily we can define. The same thing we can put it on the third option. It will be from the 12 volt I gradually step down the current. With respect to current thinking will be slowly I can step down, but the voltage will be getting stabilized or not. Like that also we can be able to see the loading effect. When you see this image, there will be the on-time effect and off-time effect. This is whenever the switching device, because we are doing the converter, the other thing will be the switching. Because of the switching effect, I told the measurement also is different. That's why we are given a delay time. Here, we are given delay time of some microseconds will be there. Because it's vector on and off and time, you see the glitches. There will be some fluctuation. There will be what called as a glitches. When you off time, the current it will be getting it immediately turn on, and your voltage will be getting dropped. That also the small transient effect in the voltage. That also we can use. If you want to avoid these things, you can use the measurement delay. Manually, if you use the measurement delay, you can avoid those steps. And coming to the end, these are all the wide portfolio we have, and we have one more important thing with the ECS group software. The software can help you to do the verification of your component. in case any power device or it is a MOSFET or the solar cell or it is a wafer or it is a IV or PV, like any characteristic we can able to see in the ECS software. Okay, this is the most effective software you can use for SME as well as the parametric analyzer. In the parametric analyzer, we have a lot of options in there compared to SMU. I can give some few steps actually. In the parametric analyzer, we can go up to, we have a solution up to 1500 amps and we have a voltage up to 10 kVA. Like that of high power devices also, we can able to test. You can see the performance of the high power IGBT of MOSFET and how the performance characteristics, IGBT, VDC, and what will be the reverse bedroom case. That is the performance and it gives the report of the sample. Like that also we can able to use in our parametric analyzer, we can do the test. And the same parametric we have both categories. One more equipment being 1500A, you can achieve the 0.1 sensor. That will be the one more important. Will be the 0.1 femtoampere. For example, with the up to ampere, you can be able to achieve. The software will be the common tool. You can use it for SME as well as the parametric analyzer. Whenever you are using the ECS software, we preloaded the application. Okay, lots of applications we preloaded in the software. There will be the BJT, or there will be the transistor, or there will be the discrete devices, nano devices, like that solar cells, like that various applications we preloaded actually. User can easily select their application and set the voltage and current and current. It gives another report also. That also is possible to do, and you can export the data and you can export the graphical representation and you can apply your own calculation. You can apply your own calculation and you can get the algorithm output in the waveform also is possible. Okay, like that effective tool is there. In just say you see the lot of categories we are mentioning. BKT, CMOS, discrete, nano, this will be the organic, and the solar cell structure, like the various combinations will be there. And the same sample you want to do multiple. For example, if you have any structure kind of thing, you want to do the VDC, versus IDC, and you want to see the power bias, or you want to see the character current, or you want to see the drain effect. You can create your own sequences, and if you run the sequences, automatically the 5 steps, if you right side, I can choose my tower. I can multiple steps and it gives the simple report. Like that also is possible using our way. And if you want to see the repeatability of the test, means you can repeatedly run the test 10 times, 100 times also, you can see the performance of your sample. That also is possible in our software. Okay. Here you see the multiple examples. Okay. You can create a own application, and in case you want to working on your different application, there will be some biomedical application also from where they are using, they want to see the characteristics of the thing, and the photonics also there they are using. Like that also, you can create your own application also possible, and you can see the IVCD possible. In IV, it will be from, I told you in the dedication. In the CV also, you can able to see from DC to 5 megahertz, we have an option for CV package. Okay. And in C, okay, this is the on-time effect, and like I said, the right side you see the user defined, and you see mostly can do the own analysis format. What is the variable 1, variable 2, like the multiple keep, and we can see the ID as well as the power flow. Like that also is possible, and the power bias, reverse bias, that sequence also we can see. This is more effective software actually. It's more user friendly also, because the preloaded categories are there, and it will be more classical represent also is possible. Coming to the summary, today we discussed about what will be the characteristics. what will be the linear and the non-linear characteristics, and what will be the IV and characteristics happening, or how to achieve the low current measurement, what are the steps we are following. You want to look at looping of the grounding effect, and you want to do the average measurement, and you can avoid the power line cycling effect, and use which cable can achieve the low current using the tracks, and what will be the tracks, what will be the difference, and how to select the range that will be reflected in the measurement, how to avoid the transient effect in the switching. Okay, these are the things we are used. It is not for the special, it will be common for all characteristics in the ID. If you are achieving the less than the nanoampere and you want to measure the high resistance, we automatically your current will be very, very less in the high resistance measurement, and the current fluctuation will be very useful to measure. If you want to follow these steps, you can easily achieve the measurement. And third will be the temperature effect in the measurement. Your sample, if it is continuously applying current, your sample will be getting overheat. Because of that, your resistance value also will change, and your interferences, how we can avoid the external interferences. There's a lot of steps we follow today. And last thing will be our software. We have two software, one is the PID, this is for basic software. It is only for operated in SMU. But in ECS for, the ECS for SMU for SMU, as well as the parametric measure. This is a common software. We can use your own sequence and give them automatic report. You can export the graphical view as well as the Excel data, and you can do the calculation, and you can do the analysis in the ECS software. Okay. And I can give some basic equipment. We have a B2900C series. In the C series, we have a single channel, dual channel, and the dedicated we have a source, not no source also we have. And the third one will be the most important thing. I want to give some input on this part, and will be the parameter to meter. The two meter is mainly used for high resistance and low current. So it's only mainly used for high resistance and low current. This is mainly for the insulation material. Using this, can go up to 0.01 femtoran, and we can measure the high resistance of beta ohms. This device, we have some special equipment. How we are achieving this means we are using the battery operated. What we discussed, the power line noise and the averaging method, a lot of things will be just that we can't avoid, because we need a power for equipment operated, we need a power. That's why in electrometer we are using the battery operated. It avoids the power line noise because the battery is in the pure DC. There is no fluctuation will be there in the DC. The kind easily we can achieve the 0.01 sometimes, and we can measure the 10 beta ohms. This is the only device in the world, the equipment operated in the battery and measure the high resistance. This is the only device in the world currently. You can know the meter in the equivalent of 10 beta ohm in the 600 basic resolution, and the 0.01 femtoampere. We can go for the range of the observation to picoampere is the range. We are getting the 600 digits, we are easily achieving the measurement. Okay. This is our portfolio. And please note down the link. This is the handbook for parametric measurement handbook. Whatever we discuss, it will be a 200 page. It will be more and more valuable in the measurement. How to achieve the measurement, what are the steps you want to follow, and what are, now I tell very less. From the book only I have given you some basic things, but in the book they have a lot of information will be there. If you want to detail, you want to go in, then go through this. It will be more helpful. It will be free only in online. You can able to download from the website. It will be effectively used in the education. Okay. Are any other questions?
Yeah, thank you very much. It was a nice session. So now we are open to the questions. So questions, which integration.
The question is that it is in the chat box also. You can start. Otherwise, you can please note
Integration.
and the later also you can contact integration anytime you can need to support.
One user is asking about integration of measurement to reduce the noise.
Yes, sir.
How to do that? So,
Integration.
What's possible to do the integration measurement to reduce the noise?
Okay. For measuring the insulation, you want to integrate your
integration measurement. This is to reduce the noise. Integration measurement.
okay. Okay. I can show in our software. I showed now. If you want to do the integration of measurement, in the software we have an option called we can give the time delay and we can set the measurement point manually. We can be able to do the step sequential data. In the sequence that we create, we can do the integration measurement very faster and we can achieve.
Can you show the slide once? I want to see the slide. I want to understand the procedure.
Okay. Integration is the resistance you want to hear.
Previous,
Hello.
previous,
That is the previous slide. There is a curve. You have shown the curve slide. Like
Yes.
AC, you have shown measurement also you have shown measurement. Just want to understand how you integrate it.
This transient you are getting correct. Okay. Yes. You can able to see the curve.
this is transient.
This is transient. Before that, before this,
One second.
before this slide, you have shown integration. You have shown some sign curves, right? Sign AC is in before this.
Okay. This one, correct?
Yeah, this one and also previous also you have shown some
Yeah. What will happen is because of the easiest way of measurement is, for example, if you have a diode, if you connect and if you do it in the auto range, then you see in the here will be the auto measurement speed will be the auto. In auto, what will happen? The measurement range will go manually switch. And it will take some time delay, but it will be not reflected in your eye because it will be happen in the microsecond. Okay. If you put it in the auto means the equipment will take care of based on the range, the equipment will take care of the speed. Okay. When you put it in the integration manually, here we have a lot of options will be there. One will be the normal integration. Normal integration means with the next one will be the long, next one will be the manual. In manual, we have options called PLC dating. Okay. In the PLC dating, we can use instrument. We have 1 PLC, 10 PLC, 100 PLC, or 0.1 PLC. Like that, we have various options. Okay. When you apply the 10 PLC, every 1 second only we can get the every 1 second we are getting 5 samples, 5 measurements from each spot. It takes the average and it is being plotted within the graph. For example, if you are speaking, within 1 second, you can achieve the ID characterization. If you are speaking on, maybe if you have time, I can give you a live demo.
Yeah. You can give us.
Okay, 1 second. I can show equipment.
How much time it will take? You mean live demo?
Maybe 10 to 15 minutes.
No, the later. Yeah. So basically.
Okay. Here the measurements will be auto. Okay. In the software, what will happen? I can start the maybe I can start the software feature. One second. My screen is visible, correct?
Yeah, correct.
Yes, I can put it in demo mode. First, you want to do storage. You want to connect the equipment. After the connecting, I want to do the channel settings. In the channel settings, and here we see lost. We have a constant. Normally we are using the variable. In the variable, I know the sample. No sample is better for higher accurate. We normally recommend minimum with the 100 sample is better. And if you drag area, and here we have option called normally with the constant flow. You can use the voltage source or current source in DC or pulse mode. Okay. So you can see the pulse and what is the on time and what is the off time. You can able to see the difference. Okay. When you put it in constant, you keep on increasing the number of steps. Okay. You can use the start voltage. And if here we see linear double or less like that, and we can give the source there also. Maybe you are so big, it will take time, or you want to do the. I told that it is a switching effect is the effect. That you can give it the source here. And here we are giving the source of the manual range. You can use the auto range and manual range. Both will be there. And coming to the last, here you can define the fees. You can here we have option called soft, medium, normal, long, and manual. When you put it in manual, you can give your time. What is the time? Whatever you want, millisecond you want to do the measurement. If you put it in the manual, then automatically your integration marks will become down. Okay, this is the important point. That's why we normally call this the manually also you can use, otherwise you can go with the log. Log means it will take average of 100 samples and it will give one sample for your measurement. That will be more helpful. And if you put it in normal, the time it will be accessed every 10 samples, you can get the average value. Okay. Defaultly using the normal condition, we recommend go with the long or short. When you want to achieve very short time of measurement, if you are using the pulse, so you are applying single pulse, you want to see the characteristics, the time using the stop. It will be very faster, it will be reflect. It will be in the microsecond. You put it in the long, automatically you will get it just 100 pounds. These are the properties. Once you put it in auto, means the equipment based on your previous test. And one more important thing, the trigger, so there is the trigger means normally if you want to see the characteristics of IV, means trigger you can put it in auto. If some people working in the solar application, that trigger they want long time measurement. Because they want to give the light intensity. Based on the light intensity, that when you turn on the intensity, the current will be increased. When you turn off, the current will be come down. That switching, that it will be look like a square waveform. That pattern, if you want to see it, you want to put it in the timer, and you can take a sample of 100 milliseconds like that. You can continuously run, maybe it will be for 1 hour or half an hour. You can see the with respect to light intensity, what will be the current fluctuation in like that also you can able to see in the graph. For example, now I put it in 100, if I run it within the fraction of seconds, the measurement will be completed. We can see the voltage, current, resistance, and the source, everything is possible. We can change the format of the engineering. We can receive voltage from the microvolt, and the current now will be the repetition demo mode as well. Will be the 9 nanoamps with it, and you can source voltage also. You can able to see. You can export the data in CSV, and you can save it in your own, and you can export all the plot, and you can give some based on the measurement. You want to do some calculation. This calculation also is important. The most important thing. Now we are saying with respect to time. Okay, you want to change it to this you give the solar voltage. You want to respect to time. You want to see the time of the current. If you want to see the voltage IV curve, you can choose the x-axis of the voltage. Y will be the current. You can get the linear. Then like that. Multiple plot also is possible because the software change software also we can control up to 4 channels. We can choose the multiple curve also is possible, Y1, Y2 like that. User defined curve also is possible. Like that you can see different channel and different graph. Okay. Are you getting now what is the measurement we will reflect? Now I put it in 10 samples. Okay, now you see the graph. When I put it in 1000 samples also, it takes time. You see able to see the fluctuation. Okay, but the fluctuation if you put it in table, you can able to see the fluctuation of the current will be very less. It will be, for example, will be in the 1 micron or 10 microns. Like that, you can able to get the measurement. This is the free software, free software. Like that, you can option into that. And in advanced setting, we have option for 4-wire. You want to do the 4-wire, if you are doing the measurement, we recommend go to 4-wire. The 4-wire only we can avoid the cable loss.
Any other question?
Is there any other doubts?
Hello?
Yes, sir.
What are the basically, are you taking another session or we have covered everything in this session only?
The writing is covered for actually. After break, the tuition will take care of it.
From your side, everything is covered, right?
Yes, sir. Yes, sir.
Okay. So, okay, fine. Yeah. Any other question? Anyone? I have a question on the connector which I have faced the real time problem from the side. I'm telling you. So let's say that the site has the coax tracks cable, the specific tracks male cable.
Yes,
And that I connected to coax female cable.
It's possible that we have a
I have
connector.
connected that. I believe what issue I faced. So basically,
Yes.
if you talk about tracks cable, it has shielding, main and ground, right?
We have 2 options, sir. Actually, in our tracks to BSC converter, we have 2 options over there. You want to make a ground or you want to make a
No, whatever tracks I have. So if you connect tracks to coax, my question is,
no.
if you connect tracks to coax, the shield will connect it to where main or ground is protein.
Yes, sir. One second, I can show the image.
You show the image of coax to tracks and coax to tracks converter. Just help me understand. You have an image of tracks to coax converter? Yeah, please show me that. And did you cover the slide for CV measurement?
So mainly we focus on the SMUs.
Okay, fine, I'll take care of it. No.
Okay.
Please show any.
One second. Now my screen is visible.
Not yet. So you should say that.
I can put it in the web.
Just try to see the converter. Try to work converter.
It is visible.
Right. Thank you.
Okay. The first one you see.
Yeah. So basically, this is track to DLC, right?
Yes.
So track to DLC converter. So you can see that CLD we have connected to ground.
Yes. Yes. That time, otherwise, what will happen is it will be floating again.
So CLD you can connect to ground. Because what I here's the problem that the same track to DLC converter when I am connected.
Okay.
And then after that I do the characterization. With my device is not probe, but still I am seeing the huge current. Means I am seeing that there is some short main to.
And the instrument also is grounded, correct? Instrument backside we have a ground tape. That also is connected.
Instrument
Otherwise, in the front we are given as a green color that we want to do the ground.
That is the problem. Okay, I'll see once again. I will have.
Okay. Thank you.
So, the audience, is there you have any more questions? No more question. Then please thank the